Hello, boa tarde, good afternoon, not good evening yet. So I don't think we need to introduce you to Fabio Cafardo. You already heard from him an overview of Fermi-LAT results yesterday. And today we will do a fun part, which is getting our hands dirty with observations of the extreme universe. Fabio?
Thank you. Well, hello, everybody. I don't know if all of you have the tools installed in your computer, but if you don't have it, it's not a problem. I'm going to show. Are you listening?
It is a problem.
Yeah, well, yeah, but you will be able to follow everything because I'm going to show the tutorial here. Oi? Ah, é verdade, eu esqueci disso. Tá bom. Okay, so if you don't have the tools there, you'll be able to follow here. Because I'm going to show you, and you can also sit together with some friends and follow with them. So first of all, just a reminder for you on how to start the tools. This is something that I showed you yesterday, but I'll be really quick today. So what we're going to do, we're going to analyze that blazar that was seen flaring together with the detection of the neutrino. Yesterday I talked a little bit about this. You probably have this link that's where you can download everything from and tells you how to install everything for the tutorial. Okay, we are going to try to reproduce this light curve among other things. We are going to use Fermi tools that are the tools that the Fermi collaboration makes available to treat Fermi-LAT data. And also Fermi PI, that is a Python software that helps us using Fermi tools. It makes them easier to use and also sometimes faster. Okay, as I mentioned yesterday, there are several things that we already have processed in the files that we made available, so we can make something in the hour and a half we have. So, okay, this is how you start the tools. I don't know if you all did that, but now it's time for us to start doing things. So you have first, if you are not using some kind of Linux, you will have to start the Docker in Mac or Windows. Then you go to the folder where you download everything. We were suggesting calling it Fermi. And then you type this on terminal, and this is going to start the tutorial. So I'm going to do exactly this so you can see. And it's going to give you, okay. Going to give you an address that you have to copy and paste. Okay, it's taken longer than I was expecting. Okay. This is the address. And now the only thing you have to do is to browse to the folder where the notebook is. So we click here in this folder, and then Blazar, and it is this file called Blazar Neutrino. Okay, so we open it, and that's it. Here is the tutorial. Everybody is following me? Someone has a problem? Okay? Okay. So I don't know how many of you has used Jupyter Notebook, but it's really easy to use, and it's great because we can add all these comments explaining what we are going to do. you'll see that there are some little things like this that are codes that we can run. And to run a code, you hold Shift and press Enter. And that's it. This one runs. And the same here. So it's just like this. If you press Shift Enter in a box where we have text like here, nothing happens. So you can hold Shift and press Enter, there is no problem. But if you just hold Shift and keep on pressing Enter to the end, you're not going to follow many things. So okay, what we are doing here? I'll get here so I can read. Okay, we'll do some analysis using Fermi PI, as I said. Here I explain what this is. Actually, most of this text is not even mine. It's a tutorial that we built based on Fermi PI tutorials. If you go to Fermi PI's webpage, you can find several tutorials there where you can learn how to use the tools. We have a link here. And we are going to work with this Blazor. So we have the right assumption and declination of the source here. We need to have, actually in this case, we don't need this information because this is a source that is in Fermi's catalog. But if you are trying to work with something that is not in the catalog, you have to use the position of the source. We are going to, yesterday, I think someone asked me about the size of the region of interest. We are going to work with 15 degrees. Actually, we're going to work with 10 degrees, but we have a 5 degrees buffer around our region of interest. So you understand it better when we start building the models. We have the time of the neutrino detection. I don't remember, it's somewhere here, but okay. But we are going to work, it is in 2017. So we are going to work with 1 year before and 1 year after the neutrino detection. So we have 2 years of data here. As I mentioned yesterday, Fermi has 11 years of data, but to make things faster, we are just going to work with 2 years of data. And the energy range we are working with is from 100 megaelectron volts to 300 gigaelectron volts. This is the energy range that they used in the paper. The link to the paper is here if you are interested. It's a nice paper. This is one of the papers that I suggested yesterday. So, okay. 300, yeah. Okay, so you remember you downloaded several things, and a few of those things are what we call events files. These event files is something that I mentioned yesterday, is where Fermi keeps all the detections, so all the photons that were detected. The information we have there is the position, the energy, and the moments of the detection of the photons. And there are, I think there were seven files with pH in their names, pH something, pH from photon. And the first thing we do is to create a list with every pH file we have. That is this Blazor file here. So in this file, what we did here is just creating a list of the photons files because we are going to use that. Instead of linking to every single one of those 7 files, we just link to one that has a list of all of them. One thing that we always have to do is make a config file. Here is just one example of the choices we are inputting in our file in this analysis. I have this here just for you to use an example. If you want to make some other kinds of analysis, you just need to follow this example. And also, you can go to Fermi PI webpage and see several other examples there. Okay? Probably the config file you have there can be wrong because we changed it yesterday. But if you have a problem, I know how to correct it very easily, and we can edit this file if you have a problem. And we are going to find very soon if the file you have is the last version or not. So, okay, let's start the analysis. First thing, there are modules that we need to load. Okay, just Shift-Enter there. And now, here is where you can maybe have a problem. We are importing that file that I mentioned, the config file that I mentioned before. It is importing and creating this GTA thing that is what is going to give all the information to the Fermi tools, like what source we are working with, the energy, the time period. I'll press Shift-Enter here at setup also, because I don't remember if the problem happens in setup or here. And if you see some kind of message saying that they don't that the software is not finding some kind of file, you tell me. Okay, for me it's working, but for you maybe it. I'll show you how to correct the file, because if you have this problem, it's very easy to correct. You just need to go to the folder where the file is. This is that Fermi folder that I mentioned, Fermi PI tutorial, and the file is inside the Blazor folder, and it is this one, this config file. And what may be wrong there, not every single one, depends on at what time you downloaded it. We may have to correct this. I'll show you as soon as it opens. Okay.
But is there anybody having this error?
Somebody's going to have for sure, because we just updated it yesterday.
Okay,
sorry?
One person is having the error. Anybody else? Two people.
Yes.
3,
okay.
4, 5.
Really easy to solve.
1,000 people are having this issue.
The problem is that we have the wrong path to a folder there. So we have to include something here in the address. Let me just. We have to input the correct address to the files, okay? So, for instance, it's hard to work with 2 screens and the one on your back. So here, this SC file, this is the spacecraft that I mentioned yesterday, the spacecraft file that tells the position of the spacecraft, where it was pointing at each time, and it has to be in the correct folder here. So the spacecraft file is here, Fermi PI tutorial, data, Blazor, and that's the address that should be there, okay? So this work dir here for me is Fermi. So I have this Fermi PI tutorial, data, Blazor, and the name of the file. So you just need to make sure that you are pointing to the correct file here. So just find in your folders where this file is, and I'm talking about this file here. Which one? This one here, okay?
This is a question to you. If you have any questions, please ask Fabio. Fabio will answer all your questions about high energy astrophysics.
Yeah.
If you want to solve Azov's equation in detail, you can ask Fabio as well. If you need to solve the general relativistic kinetic theory, ask Fabio, please. But everybody here dealt with FITS files before. Who ever dealt with FITS files before? Can you raise your hands? Okay, so just let's see, perhaps 1/3 of the audience. Okay, so a FITS file is a kind of it's a binary file, binary file format, which is unfortunately very popular among astronomers. So it's a kind of file which has a header, which has some information in a text, and an ASCII header, and then a binary where you can store a table, you can store images, you can store all sorts of things the fits file, okay? If you want, you can even open the fits file with Adobe Photoshop if you want. Even though I don't recommend doing that. Okay, Fabio, sorry.
Okay, so now you that have some problems to solve it, you just have to change the address for these 3 files and this 1 file here, okay? You have to point to this folder, Fermi PI tutorial, data, Blazor, and the name of the file is correct. You don't need to worry about the name of the file, just the path, okay? And I'll explain to you what these files are. So the first one, this one, while you are doing the corrections if you need. This one is the spacecraft file, as I mentioned, the file that tells us the information where the spacecraft was, at what direction it was pointing, and all of this. This one is the galactic diffuse emission model, a model that I mentioned yesterday several times. This other one is the isotropic diffuse emission model, the one that covers the whole sky. And this third one is the catalog. Yesterday I talked about the 4th FGL catalog. We are actually using the 3rd FGL catalog here. Is a previous version because we were having problems with newer versions of the Docker, so we had to go to a previous version, but it's the version that they used in the paper, so it's closer to the result also. So, okay, is someone still changing? Okay, can we, you are changing the path? I can go there, but okay, I'll go there in a second. After you change, you have to run this cell again, okay? Because this is the cell that gets the config file. So you have to run this again and then run setup. I'll go there to see what problem she's having. And okay, it's probably the same thing that is happening to all of you. I'll be here in a minute.
Sorry, I can
Yes, actually you don't have the files there. Go to your, yes. Are you running this at Fermi folder, at the Fermi folder? Go up. I want to see in which folder. You have to go with yes. Go all the way up. Oh, no, that's it. Yeah, you have to go to that Fermi folder that you created. Yeah, then you do all of this.
Aqui, ok.
Acho que agora você está certa.
Não veio nenhuma diferença.
Não. Então volta no seu... Isso, mas deixa eu ver. Então, ele está com problema aqui. Em que pasta que... Volta lá no config. Isso. Não, config... Cadê o config? Aquele arquivo de texto. Você fechou? Tenta colocar um Fermi depois do work year. Escreve a palavra Fermi. Isso. E aqui embaixo, naqueles 3 de baixo também.
One comment that we should make, and I think it's pretty obvious what I'm going to say, but the language for gamma ray, for Fermi analysis is Python, okay? So as you can see, this is a Jupyter notebook, and if you want to get good at doing analysis of Fermi observations, you need to learn Python if you don't already know Python. And I should note that in the future, when the Cherenkov Telescope Array Observatory will be online, CTA, when CTA will be on in a couple of years from now, probably, the software developers that are writing the analysis package, they are mirroring their software based on the Fermi software, okay? So the idea is that when you analyze ground-based gamma rays in the future, it will look very much the analysis pipeline like this, okay?
I don't know if I can solve it now because everybody will have to wait, but I'll come back here when there is things running there and I'll have a few downtime, okay? I'll come back and you'll see. Okay. I think I can keep on going, or okay. This is yesterday someone asked me what we have that is pre-processed, right? Somebody asked me yesterday. This is the step that is mostly pre-processed. You can see that we are skipping several things here. Skipping data selection, skipping LT cube, skipping. We are skipping all of this because we did that before. If we didn't skip all these things, this step would take like 1 or 2 hours, okay? What's going on here? So you can understand, and when you go do your analysis starting from scratch, you have to run this, and it's going to take a while. Here, pretty much what we are doing is this. We have the photon files, we have the spacecraft files, and now we are trying to merge them together. Because, for instance, the Fermi telescope is observing some kind of region in the sky. So when it's looking exactly in that direction, it's going to collect way more photons than when it's observing like in an angle, because and actually with not only more photons, but especially photons with better resolution, right? Because as I mentioned yesterday, if the photon interacts normally to the telescope, its resolution is way better. And now we have to combine these two informations, the amount of photons that we have with their energies and with their directions, with the information about the spacecraft. So the spacecraft was looking for this region, so the exposure in this region was higher, so it's expected that these photons have better angular resolution than the ones that we are getting in an angle. So this is pretty much what's going on. Also, we are getting rid of photons. For instance, if we have 11 years of data, if we have the data for the whole time period of the mission, like for instance, I have in my computer, I don't download only the photons that I have all of them, but I just want to work with 3 years. It goes there and crops the 3 years that I want, and don't care about the other 8 years of data. So we are doing this kind of things. Or for instance, the energy. We are only working with 100 megaelectrovolts to 300 gigaelectrovolts. So the information we have with lower energies or higher energies, we don't need them. So this step is getting rid of all this information that we don't need to use, okay? And it takes a lot of time because we have to correlate both the spacecraft information and the photon information. Okay, now we can really start the analysis, right? After all of this, we already have some some we will open it in this, and actually we are going to open only one of them. This one, this is what we call a count map. So here we have information about everything, every files that we already have after the setup step. So we have exposure map. Exposure maps is that thing that I say, the exposure is how well a region of the sky is being observed by the telescope. We have the counting cube that has several informations like direction, energy, moments of arrival of the photon. We have the lifetime cube that gives us information of how well the telescope was observing some region of the sky. And now what we are showing here is only the count map. What the count map has here is number. This is a very crude image just for us to have an idea what's going on. Later, we are going to have better images. But here what we have is, we have the count cube, we have the position of where the photons are come from, and we have this information in several energies and in different moments of time, and we are just stacking all together. So we are summing every single photon that we received in every energy between this range, and we are showing there. So we can see that there is a bright spot in the middle of this image, this is the position of the blazer. The center of this image is the center of the blazer, the position of the blazer. Disregard the axes. They are all wrong, just for us to have some image here. This is not the coordinates of the blazer. But we can see here, this is just a crude image. So we see there is something there, okay? But this is just to show you what kind of things we have in that data. And now we are going to print the region of interest. Region of interest is that 15 degrees, actually 10 degrees radius that I mentioned, centered in our sources. So what we have here is something important and interesting. We have a list of sources, including several 3FGL sources. They are all point sources, you can see here. Sometimes, depending on the region that you are working with, you will find also extended sources. And we also have the isotropic diffuse emission model and the galactic diffuse emission model. They are not point sources, of course. Here is the spectrum type of every single one of the sources in 3FGL catalog. Here's the offset from the center of our region of interest. Of course, this source, that is the blazer. This is its name on 3FGL. The offset is 0, and you can see that there are several sources as we move away. This is the TS. I'll talk a little bit about TS in a few seconds. And here, this NPRED thing is the number of predicted photons that we detected or was expecting to detect from these sources during that period of time and inside their energy interval. So we can see that the number of photons don't seem to be very high, but yesterday, as I explained to you, if we consider the 11 years of photon collection from Fermi, is less photons than these lamps emits in 1 second. So that's okay. We expect low numbers here, okay? But you see how this number is going to change. So remember that the number of predicted photons is 2,500. And now here, this print, we are just printing information. Before, remember that we are just showing what is in the catalog. We didn't make no fitting to our data, yes?
They are all different
sources, yes. Yes, yes. They are not very easy to see, right? You can't see them, yeah. Later, you are going to see them, okay? But here, what we have here is just the count maps, the total count maps. But since this source is so bright, the scale is not good enough to show the other sources, okay? The problem here is only the scale. And you can see that it's really, really high comparing the numbers, right? Except maybe for this other one, there is probably something really close here. You can see that there are two bright here. Yeah, we'll see later the source. Well, if we have time, this is something that we are going to do if we have time. Okay, so now we are printing information about our source of interest. If you want to try here, you can include the name of any one of the sources here, and you get information about it. So we have the position, we have the TS, I explained, the number of predicted photons, the flux. This is photon flux, so number of photons per centimeter square per second. Here we have energy flux, so it's in mega electron volts per centimeter square per second. It is a point source, a power law, as we saw. And here, if you want to construct its power law, here are the values of the prefactor, like the normalization, and the index. And this is a scale. I can show you this. So it's the number of photons. So what we have here, the prefactor is this one. The index, okay, we don't have this because it's negative there. And the scale is this number. We usually don't fit the scale. We let the scale the same value that it is in the catalog. but we usually fit the other two. And why do we do this? And we are going to do the fit now. Okay, let's start the fit because it sometimes takes a few seconds, and I'll explain what is going on. Let's run until this cell here, fit results, okay? So what we are doing here, the first thing, we are fixing every single value of every spectral model for all sources in our region of interest. We are only doing that so we can control really well which value, which normalizations we are going to let free, okay? So first we fix everyone, and then we start to free every single source that is 3 degrees or closer to our source, and we are freeing their normalization. So we are talking about these sources here, from this one up, okay? So they are mostly power loss. There is this power law too. I don't remember exactly the format of this. And there is one log parabola also. And we are freeing the normalizations of these sources. So we are trying to build a model. We have a model for each source that are these formats. And we are going to let their normalizations free. Also, we are freeing our source of interest. We are freeing also the index, okay? And now we do the fits. So what we are doing is fitting the models to the data, okay? We maximize the likelihood that our model explains the data, okay? There is one thing important here. There is this quality and status. Here, this is the best result you can have. So quality 3 is status 0, which means that your fitting converge, okay? It's all right. Sometimes you get like quality 2 with status, different values of status. If this happens, your fitting is not correct. You have to try it again. Usually, a good thing you do is try to fix things that are free. So if you have too much free parameters, if you have more than 10, you start getting these kind of problems. You start to fix some parameters and run again. And sometimes you get quality 2 or 1, which is bad. But when so it can be frustrating sometimes. Sometimes you have to try several times until you get a good quality in your fitting. But usually in regions like this one, with few sources, it is easier to fit, okay? If you are working as I do with the center of the galaxy, it's pretty hard. Sometimes you have to try really hard to fit a model. And later, if we have time, I'm going to show you how we evaluate if our fitting is good or bad, not only by this number, but by comparing our results in a map, okay? If we have time, I'll show you that. And now, let's print again information about our source. And the first thing is that the number of predicted counts, you remember it was 2,500, and now it is 6,000. So it increased a lot. And why did it increase a lot? Because that number, that lower number that I showed you, 2,500, is from the catalog, the 3FGL catalog. And 3FGL was constructed considering only the 4 first years of Fermi observation. And maybe you remember yesterday when I showed you the light curve, it is really low. The emission is really low for several years, and only a few months before the neutrino detection, it increased. And and the increase is the flaring. And the flaring happened after 3FGL was made, okay? After 3FGL was completed and available. So this information about the variability of the source that got really, really bright is not included in 3FGL. But then when we make a fit, we see, oh, this source is not as, its flux is not as low as we thought, at least not now. It was maybe before. So that's another reason why it's so important for you to let at least the closest sources to your source of interest free in at least one fitting procedure. Sometimes you can, actually, many times you have to do more than one, especially if you have a lot of sources. And so you have to let them vary a little bit in your models, just in case they varied along after the catalog was completed. Okay, and now we also have the information of TS here. TS means test statistic. It's a measure of a statistical measure if the source is really there, if the source was detected or not. So we are having this result, 6,000 and something. And what does it mean? Hopefully, if you take the square root of the TS, you are having the significance in numbers of sigma, right? So this source is detected with the square root of 6,000. So it is really detected. And it is so detected that we saw the source in the count map. Actually, it's probably the only one that we can really see here. Okay? And the other sources that we fitted, they also have, I think I'm not, okay. They also have values of TS now. I'll run this so you can see. I'll run this again, okay? So it's going to show you the new version of the region of interest. And you can see that every source closer than 3 degrees has a TS value, okay? The other ones don't have, because we didn't make them free. Usually, if you're trying to do a very good analysis, maybe you should start freeing these other sources also. And now these steps only, so we save the analysis, so we have this saved as fit 0. So if for some reason in another step we want to come back to this step of the analysis, we can. Yeah.
How much does this analysis depend on the capacity of our computer?
Okay. How much it depends on the capacity of the computer? It depends a lot. Okay. But especially the most time-consuming thing is the setup. That is going to take like 1 or 2 hours. And worse than that are the light curves, because we are going to do a light curve here with 20-something time beams. So it will have to calculate. It's pretty much the same analysis, but in very short amounts of time, 20-something times. And if you have several cores in your computer, you can parallelize that. Fermi PI allows you to parallelize. But if you don't have, it have to make each one, and then the next one. And each one of these take like 10 to 15 minutes. So it can take a while. But you can see that after we made the setup, every step here is really fast. You see, even the fitting for this source, because this is an isolated source, but even the fitting was fast. It was like 15, 30 seconds. But if you are working...
Maybe he's asking whether, you know, you can do this kind of analysis in your laptops. Is that what you're asking?
Regarding the free parameters, the amount of free parameters that I am considering,
Yes. It depends a little, but there is one thing that I want to include just before you say it. Never let more than 10 to 15 parameters free, even if you have the best computer in the world, because the algorithm that does the fitting, it recommends you not to use more than 10 to 15, because you start to get strange results. Okay.
Yeah. Yeah, and usually with bright sources, it's not such a big deal, maybe.
Yeah.
Well, in your case, in
my case, the source is bright, but it's the middle
it's
of
very crowded,
a lot of noise, yeah.
But why is it so slow, perhaps? Did you talk about the math of what the statistics that this is doing? Okay. So just I think it's interesting just to have an idea of what the computer is doing while you press your Shift-Enter and then your computer started heating up, you know. Why is it heating up, okay? So the reason it's heating up is because what Fabio is teaching you to do is to build up you build up a likelihood function, which basically tells you the probability of your model given the data. Okay, so this is basically what the likelihood means, and what your who here worked or studied the maximum likelihood estimator in statistics? Maximum likelihood modeling. Okay, very few people. Okay, so maximum likelihood estimator, the concept is very simple actually. If you have a model that gives you the probability of your model being right given the data, okay, assuming you pick the right model, because your model can be wrong, right? So if you are modeling using a wrong model, then all of this is worthless, okay? But assuming you have a model that you think might be correct, and you want to find out the parameters that describe for which your model describes the observations, what this maximum likelihood estimator is doing is something basically similar to this. It's taking a multidimensional surface which describes your likelihood function, okay? So here I will plot I will try to test my plotting skills. So imagine this is a multidimensional surface of the likelihood as a function of the parameters that describe your emission model, okay? Your phenomenological model. In this case, we have a power law model describing the spectrum of your blazar, but maybe you have dark matter halos, maybe you have something fancier than this. Anyway, so you have a multidimensional surface, and what the code is trying to do is imagine that your multidimensional surface has a very pronounced peak somewhere, okay? Okay, so what your code is trying to do, it's trying to find this maximum, the maximum point of this likelihood. At the peak of the surface, the set of parameters that describe the peak of the surface will be the best parameters for your model, okay? For 2 parameters, it is easy, but if you have a multi-dimensional surface with 10 parameters, okay, it's a 10-dimensional parameter space. And your CPU is frying because it's using techniques to go through this space to try to find this peak here. And sometimes there are local maxima, you know, it can be quite tricky, but the method that Fermi PI uses is very robust. Okay, so it makes sure that it samples this space to try to find this peak. Okay, so this is what's happening. That's why your CPUs are heating up. Other questions in the meantime? Yes? Oh, I don't remember. Fabio, do you remember the name of the optimizator that Fermi PI uses?
There are several optimizator. We are using one called Minuit.
Minuit, yes.
Yeah.
Minuit, yeah.
But there are others. Yeah. And you can change them with Fermi PI. You can choose between a few.
And some of them are very robust, but very slow. Okay, this is all related to how they are navigating this maximum, this likelihood function. So I think Minuit has a good trade-off between speed and performance. Performance and finding a good trade-off between precision and performance. And for people that are doing machine learning, is there anybody doing machine learning here? Okay. Okay. Can you, what are you doing machine learning for? Louder. You're using what? Oh, you use in a hands-on, not in your research. You use in a hands-on. Okay. Okay, and you? Okay, so you're doing supervised learning. Okay. Anybody else doing machine learning here? Or has done machine learning? Well, machine learning is a sexy term for statistics, okay? So if you ever done statistics, you basically have done machine learning in the past, okay? But machine learning, if you've heard deep learning, this buzzword, deep learning, everything is deep learning these days, okay? Deep learning is doing something very similar to what you are doing right now. You are actually doing machine learning here. Your notebook is doing machine learning. Deep learning is exactly the same concept that I just explained to you. The difference is that instead of having 10 dimensions, your space, in a typical deep learning application, you have a 1,000,000 dimensional space, okay? So you need to have very powerful GPUs to navigate a 1,000,000 dimensional parameter space to find the maximum of this likelihood function when you have 1,000,000 parameters varying, which describes typical deep neural networks. Any other question? While Fabio helps one of your colleagues. Any other question? No? Okay.
So now we have a few plots that are interesting, and they show the other sources that was asked. Tem, mas é que esse aqui é o...
Não tem como manter a tela sem ativar o protetor de tela, screensaver.
Okay, now we have, I think the last time I talked to you, we were here in step 15, at least in my computer, right? So we were saving the results in this fit 0. And now we have several images now about after the fitting, okay? So here we are just checking which kind of images we have, and we are showing them here. And I explained to you what they are. Okay. So this first one is the counts. Okay, here, what we have here is data, okay? Since the scale here is a little different from that one was a linear scale, and this one is not, we start seeing other sources. Like here, we can see that there is something, our source also, and there are other sources that are in the catalog. You can see here these crosses, but they are not really well to visualize, okay? A little below that, we have the model. So this is a discussion that we had yesterday comparing models and data. The model, you can see that it is really smooth, right? Because we are modeling with recipes for every single source. It's not nature here. Here we are just working with the equation that is spectral models that I mentioned. So we can compare both of them, and this is what we call a residual map. We are not showing it here, a residual map here, but if we have time, we are going to do one. But here we have something similar to that. I showed you yesterday, if you remember, about the galactic center, where we have every kind of source in the galactic center modeled, like the gas and the point sources and the extender sources, and each one had a model. Here is pretty much the same thing, but what we are showing here, the data in black, and the total model here also a line in black, and we have the galactic diffuse emission is the blue line. So maybe it's better to see in your own computers, but it responds to pretty much the most parts of the emission of that region, even though it's not exactly in the galactic plane. We have the isotropic emission. We have our source that is in green. We have some other sources. Two of them, we have the names of, three of them have the names, and the other ones are here in gray. And here, below that, we have the residuals of this model. Of course, we can make a better fitting if we free other things, if we free other sources. It's always possible to improve a little bit. But in this case, we are not going to try to improve it more than we already have. And these other two plots here are almost the same thing, but what they do is a longitudinal cut and one in latitude, and we have like if suppose, well, it's like something in this direction and something in this direction here. And what they do is that they count the photons, so it's only a number of photons. The data is in black. The model that we have, the model is the sum of all these models, but now in space, and is the line. And the diffusion emission is here. So I don't remember exactly what they mean by this diffuse thing. But yeah, how the diffuse thing is in a line, okay? So it's so bright when we consider the whole region because it's all over the map. But when we consider only a line through our source, it is lower. And the same thing in the other direction. So this is usually if there is another source that is not well modeled and this line passed through it, you can see the source pretty well, even if it is well modeled. So it accounts for this kind of little bumps. So there is probably some source or some source candidate in this region. And now we are going to read the results. So this first step is only loading our fit zero thing. And here are every source again, we saw that. And here we are observing. So here is just an example of how we can get information. We are getting information about the flux of the source. So we use flux here. But there are several other informations. You can find them in Fermi PI's page. They have a list of everything that we have. And here for our source, we have the prefactor, the index, and the scale. These are all information that we already knew. And here is the TS, we already knew that. But it's an example, you can change what we are showing here, and you can get all the information about the source. Now, we are going to make an SED. So what do we do here? Okay, here is preparing the axis and all these things, but the SED, these are the... okay, we are still not doing the SED. We'll do it. Here what we are showing is the spectral model of our source, right? It's a power law, you remember? So here is just a model. Now we want to include the data that we have, so the dots, the points with the flux. And then we do the SED. The SED is pretty easy. Here is the code. And it will take a few seconds. And they are going to overplot the model and the data. Okay, this is really strange, right? Because we have these 2 points here where the energy flux is really, really low. Maybe no, for sure they should be upper limits and not points. Fermi has the information of upper limits. They were calculated. Actually, I don't remember exactly what we have to write here, but instead of flux, you can see the upper limits of the flux for the source, so it has this information. We are going to use that here to make the plot. So we are going to transform these last 2 points, and actually these other 2, I think the last 5 points I included here, we are going to transform them in upper limits. And now we have our model, our spectral model here, and the data. We can see that the data doesn't seem to fit really, really well with this model, this spectral model. There is an extra thing that is not included here, but there is one thing that we are planning to, we will try to change from a power law to a log parabola. So if we change to a log parabola, it's going to fit way better, but we will have to make the fit and everything again. So if we have time, we will do that. Okay, and now the light curve, now it's going to take more time, but we are going to start. Okay, here's the light curve is this. We separate our time in several bins, and we can decide the size of these bins, right? The size that we want, but when we start to go to really, really small bins, we start to have very few statistics, So sometimes if we go to really small beams, we can make a light curve. So we are going to work with 30-day beams. This is the moment of the neutrino detection. It is measured here in Fermi seconds, so it's the counting seconds since, I don't remember exactly the day, but I think it's the start of 2001. Okay, here's the information. There is this website here that you can put any date, and it's going to give you back the Fermi seconds of that date. So this is the moment that the neutrino was detected. We are going to start. I'm not going to do 13 beams after, because it's going to take a while. Let's try to do like 8, 7, okay? 7. So we are going to do 13 30 days beams before the flare, the neutrino, and 7 after, okay? Here we have several things pre-processed also, but anyway, it's going to take a while. So here are the beams, and the light curve is going on. We are using this beams LC. There is this list of times, right? So the start of the first beam and the end of the first beam, and so long and so forth until the last beam here. And later, you can play with that. You can try to make beam size smaller, larger. You can start before than 30 months. You can start before 30 months before the neutrino detection. But remember that we have here just 1 year, a little more than 1 year before the neutrino detection, and I think a little bit more than 1 year after, or maybe less than 1 year. So if you try to make beams with periods before our data, you are not going to it's not going to work. You'll probably get an error message. Usually the light curves take a lot of time to perform. We have several things pre-processed. We are fitting, for instance, we are fitting this time range, so it's the first beam. And for the first beam, I think we don't have the data pre-processed in the files that we gave you. I'm not sure. But the ones that we have is going to be faster. The data of the light curves are all that folders that you have when you download it. Yes?
Why do you free the prefactor?
Yes. We have to free the prefactor, okay? Because if you don't free anything, we are not allowing our source to vary in our model. So what the light curve does, it takes the whole time, the whole period, and separates in small periods and makes a fit to each one of them. And we let at least the normalization of our source free, so we can make it get brighter or less bright, depending through time, depending on the data. Okay. Yeah, he's remembered me that the prefactor is actually it's connected to the luminosity of the source. So it's varying through time, and we have to let it vary in our analysis, okay? And also there are other things that are more sophisticated that we can do here. We can let the closest source of our source also free. We can let the index of our source free, because sometimes it can change. It can get harder. Or the spectrum can get harder or softer. So you can decide what you let free. But when you start to let a lot of things vary, it's going to take a lot of time to run. And so it is a trade-off. Sorry? Yes, actually, usually the normalization or the prefactor, you always keep free in a light curve. And sometimes, depending on the source, depending on what you think is going on and what you are trying to test, you can let the index also free. And actually, you can make a plot on the index in each time being. So you can see the index varying through time also, and then you can model what's going on. You can understand better. And now it's going to take a while, okay? Maybe it's a good time if you have any problems and you want to call me. I think it's a good moment. And after that, it's going to take like 20 to 30 minutes maybe. And after that, after I talk to everyone that wants my help, I can come back and say other things.